Chapter 4 opens up with eigenvalues and eigenvectors, and then has something about determinants and stuff like that, and then further properties of eigenvalues and eigenvectors. So it's all revolving around the idea of matrices. And if we take a look at the definition of an eigenvalue and eigenvector, we see an equation that was kind of similar to what we ended with in chapter 3. And it's similar to a Markov chain. So let's just go through the definition here. We have an n by n matrix. A scalar lambda is called an eigenvalue of A if there's a non-zero vector x such that the matrix applied to x is going to be equal to that constant or that scalar applied to x or multiplied by x. Such a vector is called an eigenvector. And then if we just want to collect a whole bunch of vectors that satisfy this, because there might be more than one, if you have more than one vector that satisfies this, the collection of all eigenvectors corresponding to that eigenvalue lambda will create what's called an Eigen Space for lambda. Okay. So the best way to do this is, or to talk more about this, is just to do a bunch of examples. And so I do want to take this equation and have you realize that the lambda is just a scalar, a number. A scalar is something that scales a vector. And this this operation is, we can look at it as a matrix multiplication, but it's really a matrix being applied to a vector. And what that means is that when you apply the matrix to that particular vector, all you're going to do is you're going to scale that vector. So that whole idea of applying a matrix to a vector is like a linear transformation. And when you take a linear transformation of a vector, a lot of things can happen. It could go to a bunch of different places, a bunch of different things. But if all it does is it scales that particular vector, then it's an eigenvector for the matrix. So how are we going to find this? What we're going to do is, this is an equation. It looks like a valid equation. The result from a matrix applying a vector to a matrix is a vector, and the result from a vector scaling a vector is another vector. So these two are equivalent. They're equal to each other, and they're both vectors, or one can look at them as vectors. So what we could do is we can do some matrix manipulation or equation manipulation to help us find this. And if we bring the lambda x over to the other side, we're going to get 0 on the right-hand side here. Now the question is this 0 vector, 0 matrix, or 0 constant scalar? What do you guys think? No. What? So if it's a scalar, I'll leave it like that. If it's a vector, I'll put an arrow. If it's a matrix, I'll put a bracket. So is it a scalar, vector? It's not a scalar. Is it a vector or a matrix? So it should be a vector. We just said that these are vectors, right? Now, if I want to further manipulate this algebraically, it looks like I have an x here. Now, can I factor out an x? It seems like I should be able to, because that's normally what I'd like to do. Can I factor out an x like that? What's wrong with this equation if I try to factor out an x? You have a matrix and a scalar, and you can't do subtraction with a matrix and a scalar. So what is our alternative? If I have a matrix, it'd be nice. I can deal with a matrix, right? So what we do, or what we can do, is introduce an identity matrix. And if we do this multiplication here with a scalar and the identity matrix, that shouldn't change this vector value, right? And so now I can write A minus lambda I and then I can just have this. So this will allow us to find your eigenvalue with the corresponding eigenvector if we can solve for this equation, if we have one or the other. Or if we have none, I suppose we can try to find it too. And we'll see how that works out. Okay? So this is going to be our equation. Our equation, by definition, that ax is equal to lambda x, is the definition that they give us for the eigenvalue and eigenvector. But if we were to find it, our working definition will be this. Okay. Yeah. So the eigenvalues and eigenvectors only work for square matrices. All right, let's do some examples. And these are some examples that I just copied from the book, so let's see if we can do a couple of these. The first set of examples gives us an eigenvector, and we're asked to find the corresponding eigenvalue. They're all 2 by 2s, it looks like, so let's see what we can do with this. So remember our equation, A minus lambda I, x is going to be equal to 0. If we get this set up, we have our A minus, and here we're looking for lambda, and the I here is the identity, so it depends on whether you're working with a 2 by 2 or a 3 by 3 matrix or a larger matrix. And then we want to simplify that and then apply it to the eigenvector that's given to us. And I guess this should be the 0 vector. So we get lambda, well, that's minus lambda plus 3, nope, plus 0, and then 3 minus 0, 3 minus lambda. Is that right? And then apply it to 1, 1. 0 vector, we got minus lambda plus 3 equals 0. And 3 minus lambda is equal to 0, which gives us the same thing. So lambda is equal to what? Positive 3, negative 3? Positive 3. So that's our corresponding eigenvalue. So you got the eigenvalue, and then paired up with the eigenvector. In this case, they're only looking for the eigenvalue. So, is that clear? Pretty straightforward. Let's do another one. Let's do the number 3 here. A minus lambda I is negative 1, 1, 6, 0. Minus lambda I, so lambda 0, 0, and lambda. We got minus 1 minus lambda, 1 minus 0, 6 minus 0, 0 minus lambda. And for this example, they gave us, for this problem, they're giving us an eigenvector, 1, negative 2. So we should come up with an equation, a couple of equations that should be the same, because if you have an eigenvector, there should only be one eigenvalue. So we got minus 1 minus lambda minus 2 is equal to 0. And 6 plus 2 lambda is equal to 0. So these should give the same result. And the first one we get negative 3 to the other side, positive, and then negative. So lambda is equal to negative 3. And this should be the same, negative. Yeah. So that's your eigenvalue for the corresponding eigenvector. Okay? Anybody started the homework? Is this like the first few questions?
Yes.
Where they just ask?
Just multiply A times the vector and see if you got a multiple of the vector.
Yeah. Yes, it would, actually.
Looks like your next is pretty man.
No, I actually wasn't going to do that, but thank you for bringing that up, because you guys know what Hal's talking about? Well, yeah, because if you take A times, apply it to the vector V, which is supposed to be your eigenvector, this should equal to lambda V, right? So if you take your vector A, 2, 3, 3, 2, multiply it with the vector 2, negative 2, so you're going to get, what is this, 2, 4, 4 minus 6 is 2, and 3, 6, 6, negative 2? Okay. This one is 6 minus 4 is positive 2? So if this is supposed to be equal to lambda times the original vector, you can figure out what negative 2 is, or what to do with negative 2 to make it into a positive 2, right? So that's just negative 1. So this would be your eigenvalue for that corresponding eigenvector, which is a lot easier than trying to solve for these equations. That's if you already know the eigenvector. If you know the eigenvector, then you're just using the definition to confirm that. Okay? Any questions? Easier. If the E vector is known. Yeah, but if you know the eigenvector, this is the work that we did over here is a little bit more work than what we needed to do. So if you do know the eigenvector, then this is the way to go. But in most cases, you're not going to know the eigenvector. So let's take a look at another set of examples where this time we have the eigenvalue, and then we just have to find the eigenvector, which is more likely to happen. So what we want to do is that we want to show that lambda is an eigenvalue, and then we want to find one eigenvector corresponding to this eigenvalue. So let's see if we can get this set up. Again, we'll set up that the equation a minus lambda I. Well, we know what lambda is, right? So we might as well put 3 in there. Times some unknown vector that we're going to find, set that equal to 0. So we have 2, 2, 2, negative 1 minus 3, 0, 0, 3. And this becomes negative 1, 2, 2, negative 4. So we're essentially looking for a solution here. We're looking for a vector in a null space of this thing because it's set equal to 0. So we have minus x plus 2y is equal to 0 or 2 minus 2x minus 4y is equal to 0. And if we notice, I guess we should have done row reduction, right, if we're going to solve for this anyways. If we notice that if we do a row reduction, if you multiply this by 2 and then add it to the second row, you'll see that this whole row will disappear. I mean, these two lines are exactly the same, so we're really just working with negative x plus 2y is equal to 0. So let's see, x is equal to positive 2y, is that right? So if we want to find a solution for this, we'll let y equal to a variable, a free variable, so x is equal to 2t, and then we got xy is equal to t times 1, 2. 2, 1. So we have a vector in the Eigen Space. And so we just have to make sure that that's that should work. Let's see if that'll work. Well, let's see. Let's work it out and see if 2, 1 is in fact the eigenvector, or if it needs to be scaled appropriately, because it has to fit this eigenvalue 3. So we got 2, 2, 2, negative 1. Apply that to 2, 1, and we get 4 plus 2 is 6. And 4 minus 1 is 3. So it looks like it worked for us, and we found the actual vector. So sometimes we'll have to do an appropriate scaling to make sure that we get the right value. Okay? Yeah?
Can we always row reduce before we do that now?
Yeah, probably. We should have just done the row reduction, because remember that this thing is solving for this equation is equivalent to just negative 1, 2, 2, negative 4, 0, 0. It's like the augmented matrix, right? So that's really all we're doing. All right, let's do one more. We have A minus lambda is equal to 1, so we just need the identity. So we got, can I just do this together? So 0 minus 1 is negative 1. 4 minus 0 is 4. Negative 1 minus 0 is negative 1. 5 minus 1 is 4. So you see that when you do have an eigenvalue, when you have your eigenvalue figured out, then you're always going to have a null space. For a 2 by 2 matrix, your null space of at least 1. Okay, so we have minus x plus 4y is equal to 0. So x is equal to 4y. So let's see, x is equal to 4t, and y is equal to t. So it's 4, 1 is your eigenvector. And just do a quick check. Um, 0, 4, negative 1, 5 applied to 4, 1 will give us 4, and negative 4 plus 5 is 1. So that does work out. All right.
That is your Eigen Space.
Well, they want just the eigen. I just wrote this as x. This is your eigenvector.
All right.
And if you want the span of that, that will be your eigenspace. Span of this 4, 1 vector is going to equal your Eigen Space for the eigenvalue 1. I think it was denoted as E sub lambda, whatever lambda is. In this case, lambda is 1. Okay, good. So, I don't know if you guys missed your finite spaces, but we didn't do any finite spaces in the last section. Here it goes. Let's do one now. Let's try to find an eigenvalue for these matrices in these corresponding spaces. And you know what? Before we do that, let's actually find some more eigenvalues and eigenvectors. This time, let's take a look at a matrix without knowing any eigenvalues or eigenvectors and see if we can find all the eigenvalues that are associated with this. So let's do this as an example where we have to find eigenvalues. And eigenvectors. So this time we don't know the eigenvalues or eigenvectors, so let's let the eigenvalues be lambda. So we have A minus lambda I, and that's going to equal to 0, 4, negative 1, 5, minus lambda, 0, 0, and lambda. And we got minus lambda, positive 4, negative 1, and we have 5 minus lambda. So we want to find the null space of this thing. So we have minus lambda, 4, minus 1, 5 minus lambda. And then if we try to do some, what do you call it, row reducing or whatever. Oh, did I really want to do this? I want the inverse of this, don't I? I suppose you can. You'll have some weird stuff happening. I think it's more convenient if we row reduce this. I mean, if we take the inverse of this. So here's what we have here. We have A minus lambda I x is equal to 0. No. Oh, I just... No. I don't know. I'm getting lost. No, we don't want the inverse. What am I thinking about the inverse?
You want the determinant, right?
I do, but why do I want the determinant? We haven't.
Because the determinant 0 is not invertible. It has something in the null space and it's not invertible. And I don't remember whether we studied determinant.
Well, it's in the next chapter, so maybe I'm jumping ahead a little bit too much. Because,
If they gave you this problem, they must have some way to solve it.
well, they didn't give us the problem like this. They gave us a.
It's in the,
Row reduction should be fine.
Okay, let's try the row reduction business and see if it works out. But yeah, we haven't done the discussion on linking this into determinants is in the next section. I think my mind was jumping ahead a little bit. There is. I'll just wing it from here. So, I think what we want to do is if you want to get an actual vector here, so we want the null space of A minus lambda I. We want the null space to be non-zero. So remember the null spaces of our vector spaces, in this case we're in R2. The null spaces are either the 0 vector only, a line that passes through the origin, or all of R2. And if we want to obtain a vector out of this equation, then we want the null space to be not equal to 0. So we want our determinant, we want to know when a determinant equal to 0. So the determinant of this thing do you remember how to find a determinant? Well, no, that's the inverse, just the determinant. So not 1 over. The 1 over part is the. So the AD. So minus lambda 5 minus lambda, and then negative of this, and this turns out to be, what does this turn out to be? This is lambda squared plus 5 lambda minus 5 lambda, and positive 4. Plus 4. So if we set this equal to 0, then we're going to be guaranteed to have our null space to be not just a 0 space, but something else. And we're going to get, can you factor? We can factor this, right? 4 and 1, negative 4, negative 1. So lambda is equal to 4, lambda is equal to 1. So you have two eigenvalues So you have two eigenvalues for this matrix, 4 and 1. And the idea is that for each of these eigenvalues, you should be able to find the corresponding eigenvector. And what happens when you put 4 or 1 into this equation or into this matrix is that you're going to have rank 1, or you're going to have a null space of 1. So let's take them one at a time. Lambda is equal to 4. So you have minus 4, positive 4, minus 1. 5 minus 4 is 1. And so clearly you can see the relationship here, right? You get minus x plus y is equal to 0. So y is equal to x. So that gives us an eigenvector of 1, 1. If you let y equal to t, and then x is going to equal to t, and then 1, 1. Is that okay?
1, 1 is the eigenvector.
Yeah. So for lambda is equal to 4, your eigenvector, your corresponding eigenvector is 1, 1. And then now you have to find your corresponding eigenvector when lambda is equal to 1. So that's minus 1, 4, minus 1, and then you put 1 here, you get 4 again. So we have minus x plus 4y. Can't we just do this? So x is equal to 4y. And then your corresponding eigenvector then would be 4 and 1. So when lambda is equal to 1, your eigenvalue is equal to 1. Your eigenvector is 4, 1. Well, they have to be. It has to be together. For an eigenvalue, there has to be a corresponding eigenvector.
Right, but I mean, the eigenvalues don't. I guess I don't know how I'm trying to ask this. Can you
They could.
Values at the same time? Is it,
Yeah, if you're looking at the thing, we'll take a look at a picture of this particular example when we get to the picture part. All right, and the next thing I wanted to do was, should we do this? Okay. Was to go into a finite space and see what happens. Find all eigenvalues of the matrix. So now that we know how to find eigenvalues, which is to find the null space of that A minus lambda I business, we'll do that also. So they're both in Z3. Let's do number 31. So we set up the same way we would normally set up. And this would be 1, 0, 1, 2 minus lambda times 1, 0, 0, 1, which gives us there is no minus in Z. Let's just do this operation and we'll translate it once we have the equations. So we're going to have 1 minus lambda uh, 0, 1, and then 2 minus lambda. And if we're looking for, I guess we can translate now. Should we translate now? Well, so remember, to find the eigenvalues, we want to make sure that this is, we want a determinant to be equal to 0. So we find the determinant. And that's 1 minus lambda, 2 minus lambda, minus 0. What's this turn out to be? You got 2 minus 3 lambda plus lambda squared. All right. So now that we have our quadratic, let's see if we can rewrite our pluses into Z3. We have a negative 3. What's a negative 3 translate to in Z3? Translate to 0, right? So that is going to make this disappear. We got 2 plus lambda squared is equal to 0. So we want to essentially solve for lambda squared, or for lambda. So what do we add? What can we add to 2 to make it 0? Well, in Z3. So 1, right? So 2 plus 1 is going to be equal to 0 in Z3. So I need to add so that must mean that lambda squared is equal to 1, and what times what is equal to 1? What times itself is equal to 1? So lambda has to equal 1, or probably not negative 1. Or 2?
You have the factorization up there before you multiply it out.
Oh, right there also, huh? So it turns out that 2 times 2 is 4, which is in Z3, which is equal to 1.
So you really went to the negative.
I guess, yeah, because this is 0, right? So here are your eigenvalues. We got an eigenvalue of 1 and an eigenvalue of 2. All right. They didn't ask for an eigenvector, so let's just not worry about that. No. You can try to find it. The book talks about a picture, a way to picture this. That's kind of interesting. And the way to picture this is to first look at the relationship with what happens to the definition of what an eigenvector is and an eigenvalue. And here what they're saying is that when you apply a matrix to a vector, it's going to be that same vector scaled at some value, with some value. Does that make sense? So, say, given a vector x, ax, it's a linear transformation, right? Because A is a vector, or A is a matrix, and when you apply a vector to a matrix, you're essentially applying a linear transformation. That takes a vector to another vector. Linear transformation takes lines to lines, except for those people who were really meticulous and said that the 0 was a linear transformation also that takes a line to a point. So a non-zero linear transformation takes a line to a line. And so what that means is that it would take your vector, it would take a vector and transforms it. So AX gets transformed, MED, transformed into another vector that is going in the same direction or the opposite direction, that is collinear. So there's a nice, interesting drawing in the textbook where they have a bunch of vectors pointing in all kinds of directions, and then what they do is they just take those vector x's.
What you just wrote, I see what you mean. It applies only if X is an eigenvector.
Yeah, for eigenvector, given an eigenvector. So they'll be pointing in the same direction, or the opposite direction, but as long as they're pointing in the same sort of direction. So if you had a vector x like that, then AX should look something like this. And usually what they do is they put it head to tail, tail to head, so that they can see that if it's generally pointing in the same direction, and this isn't really drawn like that, we'll just pretend that they're pointing in the same direction, then it's an eigenvector. Whereas if you take another vector and then the AX points in a slightly different direction, then this is not an eigenvector. So if this was drawn right, keep drawing it black. So this would work for 2 dimensions, and if you try to do it in 3 dimensions, it might change because it's possible for an eigenvector, an eigenvalue to have an eigen space of dimension 2. So that'll be a little bit different.
So for the first one, if it was facing the opposite direction, it was still on that line.
Mm-hmm.
It would still be an eigenvector.
Yeah. So if you had another vector that's pointing in the exact opposite direction, that would still be an eigenvector. So I got this Mathematica thing that I just programmed this morning. Where I take a sampling of vectors, right? And then now if I want to apply this matrix to it, and I'm going to connect the new vectors on the heads of these vectors, then I would get something like this. These are the drawings that we see in the textbook. And you kind of look close and try to imagine which of these vectors are collinear, and I'm comparing the red and the black vectors. And this is for the matrix. What's the matrix again? Something, 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 something. 2003. And so if we look carefully, and you kind of have to look carefully, this one and this one looks like they might be collinear, and then this one look like they might be collinear. Everything else if we look at another matrix or another vector, they don't look so collinear there. It looks like it's just, well, the black ones are random vectors. The red vectors are vectors that I got when I applied this matrix to it. What?
2003. Does that translate into a whole bunch of straight black lines in a circle?
No. The straight black lines in a circle is independent of the matrix. So when I did this, these are just going to be my sampling. For example, if I wanted just 4 vectors, that's kind of boring. 8 vectors. If I just wanted 8 vectors, these are my sampling vectors, and then these would be the vectors that I would get.
So you essentially chose a vector length that was divided in a circle into 8 equal parts?
Yes. Yeah. So I took, I used trig to go around in a circle, and if I wanted 100 vectors, for example, and then I wanted to see how the attachments would look like, how you just get some nice designs. So this would be, if you just take a look at those 4 or those, if I just want to keep it simple, I'll just have 8 vectors to look at. And I can clearly see that those 2 vectors. So it looks like my eigenvector could be 1, 0, and 0, 1. That would be corresponding to an eigenvalue, and I could probably find my eigenvalue easily from multiplying things. Right? Can you find the eigenvalue? So if you just apply this, we'll see. We'll get the eigenvalue of 2 and 3. So let's take a look at the ones that we were working on. Let's take a look at this matrix, 0, 4, -1, 5. We had a couple of eigenvalues, 4 and 1, and we had eigenvectors of 1, 1, and 4, 1. So let's see how that plays out in our drawing. What was it again? This is 0, 4, -1. 0, 4, -1, 5. I guess with 8 vectors isn't. Yeah, I'll probably need some more. It looks like the -1, 1 or the 1, 1 vector looks like we got one already by luck. And so to try to get this, we need to get more vectors going. So let's go to 20, no. We had, what did we had last time? 24 or something like that? That looks okay. Let's see if we can. This isn't helping much.
It's a really interesting picture, though.
Yeah, it's a nice picture.
So they can whip around that fast, but they must. Is there some point where some of those vectors are pointing to the upper left? You just happen to skip over it, or is that what it is?
No, that's probably. It's 200 again, just to see.
Yeah.
It's a good thing Mathematica is a lot quicker now. When I first started to use Mathematica, something like this, you press click to run, and it'll render, and you go out and have some lunch, and then come back, it's almost done. Here we get things instantly. No, that's not that old. I'm not that old. So I think 2436 would be a good size that we can take a look at and see. And it's kind of hard to find that that vector, what is it, 1, 4, as part of this. So let's see let's see if we can come up with this information. We're dealing with a matrix 0. What was it again? There he goes. So taking a look at this matrix, we found vectors 1, 1, and what is it, 4, 1? So with our drawing, we can kind of see now this is even hard to see here. I was going to say we can clearly see. Okay, it's not so clear. So let's trim it down to. Remember, we had 8 vectors, and it came up really nice. So let's do 8 vectors. Actually, I'm going to change my scheme here. And skip over this bunch of circles. So this is a nice telling picture that gives us one of the eigenvectors clearly. So if we look at the 1, 1 vector, it looks like it turns out nicely over here, and we can see it clearly. So what I want to do is I want to see what's up with the 4, 1 vector. How come we can't get that? And what I want to do is I want to scale this and make this into a unit vector. So how do I make this into a unit vector? The magnitude. So what's the magnitude of this thing? Do you guys remember that? 17? So by the way, you'll need to remember that sometime soon, this whole idea of making a unit vector out of this. So let's get an approximate theta for this, because I'm working with theta. I suppose I can just plug this in, right? Why don't I try that? Like if this was a cosine and sine. Well, you guys try to figure that out, and then I'm going to see if I can just do another different graph here of my vectors. Instead of making a table, arrows, why don't I just make a table of, what is it, 4, 1? Actually, yeah. So actually you don't need a table for this. And then sorry for all this weird looking code. Uh-oh. get a little point. Do I get a point?
Or is that a red point?
What?
Is that a red point for anything?
Yeah. Wonder what that means. It's just a dot. Is that good? It's supposed to be 4. What's the eigenvalue for this eigenvector? Was it 1 or 4?
Those are one.
It was 1. So, what am I doing wrong here? So I start with 4, 1. Ow. I've been giving you half the sizes. This is what it should be, plus. Sure, that'll work. All right, so I think I've been doing the not quite lying, but my program here, I wasn't starting from the tail. I was starting from the origin again to get you the thing, and so. They look nice. All right, so here it goes. This is a little bit better. What if we go 36 again, and it's still hard to find 24? Yeah, in that neighborhood.
Yeah. I think it's 4, 1 almost. 1 just above 4, 1.
All right, so I'm going to add on these arrows here. Wait. 1, 2, 3, 4. 4 clicks. And I'm going to color it blue and purple. So if we, yeah, it's there. Well, this is because I know that my eigenvalue is 4, 1, and so it wasn't multiples of 4, was it?
I mean, you were using the 36 and
24. Oh, just because I wanted out of 360 degrees, and I want it to be nice and even. All right, so let's see if we can do this again. So the 1, 1 looks fairly clear that it looks like it's straight. Over here, it's harder to see, but at this 4, 1 business, we have another vector that is whose A times this vector is going to be some multiple. It's not just a multiple in this case, it's actually equal to 4, 1. So that can show the eigenvalues and eigenvectors. So I don't know if you have any homework that has these pictures, but if you look through the book and you see these pictures, what you're looking for are those within the unit circle, you're looking at the vector that's in there, and then outside of the unit circle, you're looking for the vector that is going in the same direction as the vector that's inside of the unit circle. So that helps you find.
What about when there aren't any eigenvectors?
If there aren't any eigenvectors, then you're not going to see. You're not going to see anything that's pointing in the same direction.
But,
Can you give me an example that doesn't have any eigenvectors?
the matrix, first row is 1, 1, and then negative 1, 1.
Am I off by parentheses? So 1, 1, and what?
Negative 1, 1.
Negative 1, 1. So if we take a look at this as an example of a matrix, and we take a look at these, the inside of that circle, the unit circle, we have the outward going sample vectors, and then at each one of those sample vectors, none of them look like they're going to be parallel, right? So this is an example, this is a good example of something that does not have any eigenvectors. And then if you work it out, then. This would be a nice picture if we have like 100 of them, huh?
Well, I was thinking these pictures seem like a really nice way to kind of look at what the effect of the matrix is. You've got like where the bulbs go and how big is it and how fast does it swing around at various points.
Yeah.
Do people do that? Is there some place where you can go and I don't know, look at this stuff?
Well, this idea of they call it an eigenpicture was written in some sort of journal of math somewhere some time ago. It's in the book.
I've seen something online where it's dynamic, so you can see the things sweeping around like a clock hand. And
Yeah.
And then the AX is kind of sweeping around in various ways.
We could do that. Let's see. We're just killing time now. Oh, doesn't matter what it's used for. It's just cool.
Like if you're on a Word document and magnify it or something, does that apply?
You know what? I don't know if I can do this off the top of my head, so I'll try to do that nice drawing, manipulating thing. So in general, you should be able to. Oh, we didn't get to do one problem I wanted to do. No, we're negative 2 minutes past, right? So. I thought it ended at 1:55.
Yeah, it's 2 isn't it? Like sometimes it's 155, but I'm pretty sure it's 160. I've been letting it slide.
No, the next class starts at 2:10.
No, I'm looking up at what web schedule right now.
All right, so real quick, let's find the eigenvalues of this. To find the this is number 35 in the book if you want to follow through it. So A minus so we want to do the subtraction. We get A minus lambda, B, C, and then D minus lambda. Okay? So remember, if you want this to be an eigenvalue, we need the determinant to be equal to 0, so that will ensure that there's no inverse. And then If there was an inverse, then the null space would just be 0, 0. So we want it to be we want the determinant to be 0. So we multiply A minus lambda, B minus lambda, minus BC. And then if we FOIL this out, we're going to get lambda squared. We're going to get negative A lambda minus D lambda, and then plus AD minus BC. And if we break this up, let's do the minus A minus D lambda, and then AD minus BC. Where? Oh, plus. Yeah. So these two quantities are actually part of this matrix. I don't know if have we talked about the trace in this class?
Yeah.
So trace equals sum of diagonals. Really easy. So in this case, it's A plus B, or A plus D. So that's the trace of A. And then this should look familiar. This is the determinant of A. And so we got the equation is equal to lambda squared minus the trace of A lambda plus the determinant. And then that's equal to 0.
Sum of what?
The sum of the diagonals of a matrix. And so to show part B, all you have to do is do the quadratic formula on this equation equal to 0, and then show that the trace and determinant of matrix A are given by these things. So once you find lambda, it'll be interesting that should be easy enough to deduce. All right, so that's it. Now it's really 2 o'clock. You mean I've been letting you guys out 5 minutes early the whole time? All right, sorry about that.